So, because she is borrowing, she wants the lowest interest rate. So, which one's a better option? A. Yep. She is borrowing. So, she wants the lowest interest rate, which is A at 6.13%.
So if she was investing, she'd want that.
Yep, if she was investing, she'd want the other one, definitely. So we've got two rates. We've got the nominal rate, which is the rate we are given, and then we've got the effective rate, which is actually what we are using, what it is actually multiplying by, increasing or decreasing by. That's why it's called effective, because it's making it happen, it's working. This is the one that is being effective at the moment. Any questions about that one? All right, cool. Pardon me. If you look up here, these are some instructions for your calculator, which we can do this whole thing on your CAS. So, looking at the next example, I'm just going to leave those instructions up there, but examples on the next bit. So, Marissa has $10,000 to invest. She chooses an account that will earn compounding interest at the rate of 4.5% per annum, compounding monthly. Calculate the effective rate of interest for this investment, correct to 3 decimal places. So what you need to do on your main screen, so not in Financial Solver, on your main screen, you need to go to Action, Financial, and Interest Conversion. And then go down to this one, Convert to Effective. That's what that means. So then you need to put in your brackets. So the first thing you need to put in is the number of compounds per year. So for this example, she's compounding monthly. So the number should be 12, comma, and then the nominal rate. What rate have we been given? Yep, 4.5. So that's what you need to have in your brackets. 12, comma, 4.5 bracket. And it should give you the effective interest rate. What did we get?
4.594.
Yep, perfect. Oops, 5. So the effective interest rate is 4.594%.
If you don't put the receipt, will you lose marks?
If it's talking about rates, then you may. Yeah. So that does the exact same thing as this formula here. The exact same thing.
And then you just put M and R in and...
Yep. They both calculate the effective interest rate.
Which one is more likely to be on the exam? Like the formula or calculator?
I would get used to using both. If there might be a question that will say something like, prove that the effective rate is 4.594. If it says prove, you need to show you're working. If it just says what is the effective interest rate, you can just shove it into your calculator.
If it's multiple choice, can you just put it in?
Of course you can, yeah. So this one's much quicker, much less likely to make mistakes, probably more safer, but you need to know how to do this one in case you're asked to prove or show you're working, or you've been given the effective interest rate and you need to solve for what was the nominal rate or what are we compounding by. Does that make sense? Mm-hmm. Yep, so we need to know how to do both. That's why I showed you both. Cool. Any questions? Nope. All right. Are we good to move on to 9A, which won't take us long, promise, because it's pretty much stuff we know. Ooh. All right. Can I rub this off?
How do you get rid of E if it says E equals 21? I think I got it wrong again.
Okay, you haven't been over 100.
Oh my god.
Oh, you have.
No, I just already did it.
Yeah.
It's like entirely. Is it because this is doing parallel?
No, it didn't when I did it. Okay, we'll get through these notes and I'll come have a look at your calculator. What's going on? Okay, so starting chapter 9.
This how many periods is it?
1.
Is it long?
Oh, I haven't seen it.
Okay.
We haven't made it yet. Okay, so 9A, combining linear and geometric growth and decay. So sometimes we will come across situations that include both linear and geometric growth and decay. So the recurrence relation for these types of relationships can be modelled by this recurrence relation. So always starting with our V0, which is always our starting value, and then we've pretty much just smushed both of them together. We've got the geometric bit here, and we've got the arithmetic bit, or the linear bit there. So we've just got our ratio at the start, and our difference at the end, depending on whether we're going negative or positive with our difference. Any questions about that? So that's what the recursion relation will look like. Yeah?
When you have a question on the test, will it state like which formula you need to use? Like will it be obvious or?
No, you'll probably need to pick it. Yeah. So write down the sequence generated by the recurrence relation. V0 equals 3, Vn plus 1 equals 4, Vn take 1. So let's go for the first 3 terms. Pardon me, using recurrence. So to find V1, we're using our recurrence relation. So we've got 4 times Vn take away 1. And our Vn is 3. Yeah. So 4 times 3 is 12, take away 1 is 11. So our first, or V1 is 11. Then to find the next one. Same thing. But we're now using the previous term in here because it's recursion.
Would you put V1 in the first line then?
Yep, you can put V1 in there, yep. And you put V0 in there if you want.
Times 11 now as well?
Yep. What did I just put? Oh, right there. 43.
If it says sequence, how many do we need to write?
It will usually say, let's just do the first 3.
Okay.
It will usually tell you though. Oh, Alright, if it says write down the sequence, we then need to actually write down the sequence. So 3, 11, 43, 171, and it continues.
So for this one, do you show you working out?
Yes, because it says use recursion.
Okay, cool.
Even if you're just putting in these 2 lines, that's okay. That's fine to just put in those 2. Any questions? So it's pretty much exactly the same as what we've done with geometric and linear. We're just sticking them together. All right, can I move down? Cool. All right, we'll just move a little bit more. So usually we will be using this with money, but just to demonstrate what we're doing it not with money, just so we can see how it works and what happens. But 99% of your questions will be to do with money. Okay, the number of trout in a fish farm pond after n months can be modelled using the recurrence relation V0 equals 10,000, Vn plus 1 equals 1.1 Vn take 3,000. So use the recurrence relation to determine the number of trout in the pond after 2 months. So remember, this is months as well that we're talking about, not years. So we've got V0 equals 10,000. V1, if we wanted to do this just on our calculator, pressing, what would we enter in? Yep, so you'd enter in 10,000 first, and then what would you put into your calculator? Yep, good, times 1.1 minus 3,000. Yep, and that would give us our V1, which would be 8,000.
How do you know that that's for months though?
Because it says so.
Oh, okay.
Yep.
So you don't have to divide it by like 12?
No, because it says it's for months.
Oh.
If it did say years, how many in 2 months, then yeah, you would divide, yep. And then we've got V2, so you can just press enter again.
Do you have to write trout after the numbers?
In your final answer,
Okay.
right, trout.
For the next one, would you still keep timesing it by 10,000, or would you add in the next?
Not timesing it by 10,000, but you would
Oh,
just times it by this bit and then keep doing it.
Oh.
Make sense?
So for that one, would that be for V1 it's 10,000, but then for the next one?
Next one, it will be 8,000. So after 2 months, there will be 5,800 trout. Next question, after how many months will there be no trout left in the pond? That's when you can just keep using your calculator, go enter, enter, enter until you get there. So we should end up with V3 equals 3,380, V4 equals 718, V5 equals negative 210.2. So after which month will there be no trout? The 5th. Yep, because in the 4th, we still have 718. Remember, this is only calculated at the end of each month. So it is the 5th. After 5 months, there will be no trout left in the pond. So when we are doing combined, geometric and linear, if we were doing these separately, so if we were doing just this bit, what would we expect our numbers to be doing? Increasing. Why? Yep, because it's bigger than 1. We've got a 1 in front of the decimal. So we would expect our numbers to be increasing. If we were doing just linear, what would we be expecting from here? It would be decreasing. So if we've got an increasing and a decreasing, sometimes we don't know what's going to happen with our numbers when we combine them. Sometimes, even though if we looked at just this, we'd be like, well, that should increase. But if we're decreasing by more than what we're increasing, overall it's going to decrease. Yeah.
How would you know when you need to combine?
It will tell you. It will give you a recurrence relation where they're combined. Any questions? Cool, that was nice and short, that one. And that's it for 9A.